Hello, everyone. Welcome back. And today we are going to be looking at the types of control systems. Now, if you remember from our previous sessions, we talked about what control systems are. And we said a control system is a system that is capable of controlling the operation of another different system. Now, that control system can regulate itself and can also regulate other systems. So it's basically a device or a set of devices that can manage, command, direct, regulate. All these are just synonyms for control in this context. So it's a system that can control the behavior of another device or system. And we have a block diagram that shows a control system where you have a process. It could also be called a plant, which is the operation of the system you want to control. Now, that process or plant takes in an input and gives you an output. And sometimes the output you get might differ due to various reasons, such as nonlinearities, disturbances, maybe wear or tear in the device or in the plant or some components of the plant. And that is why you need a controller to ensure that the output you get is in line with the input you are providing. Now that controller takes in an error signal, which is a difference between the input provided and the output obtained. And that output is measured using a feedback process. So that this diagram represents the operation of a control system. Now you have various types of control systems, right? You can classify them into different categories. You have natural and man-made control systems, manual and automatic control systems, open loop and closed loop control systems, linear, non-linear control systems, time variant, time invariant control systems. And as you would see later on, there are also other classifications of control systems. So let us look at one of the classifications, natural and man-made control systems. So a natural control system is a system that happens biologically, just similar to our natural universe or the human body. It's a biological control system, not created by man itself. However, man-made or artificial control systems are systems that are created by human beings, such as control systems found in vehicles, control systems found in aeroplanes, and control systems found in robots. Now, another category of control systems are manual and automatic control systems. So in manual control systems, the operation of the control system is done manually by an operator. So you think of temperature regulation using a fan. Our fans have regulators that you can tune and turn the knobs to control them. So that's a manual control system. You can also think of water level control, where you have a valve that controls the flow of the water coming in and out. Then you have automatic control systems where you don't need human intervention or an operator. It works automatically. So think of temperature regulation now, but instead of using a fan, you think of air conditioners, AC systems. They have a temperature regulation based on the outdoor temperature. They can regulate what is happening within that environment. And then you have the human body also that regulates its temperature automatically. So even though it's a natural control system, it's also an automatic control system. Then another category you have are open loop control systems and closed loop control systems. So in open loop control systems, they use a controller to obtain the desired response. But they do not measure the output in this instance. It does not have a feedback mechanism. And therefore, the output has no effect on the control action. So the output is neither measured or fed back into the control system. So it only takes an input and based on various calculations and assumptions provides the control signal without measuring the output. So you can see that it's just the input going into the controller, the control signal going into the process and getting an output with no feedback. So examples are your washing machines, your toasters, your electric fan. If you look at your washing machine, once you set the type of washing condition you want, maybe gentle, maybe hard or tough, it does not measure the cleanliness of the clothes. It doesn't measure how dirty the water is. It just applies that action with the expectation that that action is suitable enough for the operator. Then the same thing with your toaster. Once you put a setting, it doesn't measure how soft or how hard the bread is. It just applies that action and you get an output. And the same with an electric fan. It doesn't measure the speed of the fan. Once you apply that setting, it is expected that based on the design, that setting would relate to the kind of output you are getting in the fan. Now, open loop control systems work with the reference input. It's not measured with the output. There is no feedback. So you have a fixed operating condition. And that means the accuracy of the system depends on how good you can calibrate the system or how good you can design the system. Because you have no way to adjust the performance of the controller based on the output. You have to design it properly to make sure that when you have a particular input, it can give you the right output. So, and this means that the systems would be severely affected by disturbances, variations in environmental conditions or operating conditions, non-linearities, and so on, without any mechanism to adjust the kind of control signal gotten from the controller. And now that leads us to control closed loop control systems. And these utilize feedback so that they can compare the actual output you are getting to the desired output that you want to get, which is based on the input. So you can see that instead of just the controller taking an input, the output is measured using some form of feedback, and that output is compared with the reference signal or the input, and you get an error signal. That error signal is now fed into the controller, which provides an appropriate control signal for the process. So examples are your refrigerator, where if you want a certain temperature, you have a temperature measurement sensor within the fridge that can feed back the difference between the desired temperature and the actual temperature you're getting. And the same thing with some of our electric irons. So this closed loop system ensures that a desired relationship is maintained between the output and the reference signal. And that is done using by comparing them and getting the error signal, which is used and fed into the controller to give a control signal. So if you look at another example, a servo system or a servo mechanism, where you have a feedback control system and the output is position or velocity or acceleration, then you can have a sensor. Maybe if you're looking at position from the diagram, you can have a position sensor. When the position is not where you want it to be, there would be an error, and that is fed into the controller, which would adjust the position of the motor until the motor is exactly at the position that you want it to be. So this is just an example of an antenna positioning system. Now you can also classify control systems as linear and nonlinear control systems. So if the output varies linearly with the input, then it is a linear control system. So you have an input going into the process and it varies, or it has a linear relationship with the output. So if you look at this equation, y of t is equal to minus 2ut plus 1, and you plot this on a graph, you have a linear relationship. You can see it's a straight line. You have another example, y of t is equal to 3u of t plus 5. This also, when you plot it on a graph, you have a linear relationship. So that's what linear control systems are characterized by, that linear relationship. Now, linear control systems do not exist in practice because most physical or real world systems are nonlinear inherently. So these linear systems are just ideal models that are fabricated by those doing the analysis, because it's more simple to analyze and design. The calculations also are easier. They don't really have that high computational complexity when you compare it to nonlinear systems. So, but the magnitude of the system, of the signals in the linear control systems are limited, because every system that is nonlinear within a certain operating condition operates linearly. So that's how you can make it easier to analyze nonlinear systems using linear techniques. Now, these linearity conditions are reflected using some properties. So the first one is the additivity property, meaning if you have x1 that gives you an input of y1 and you have x2 that gives you an output of y2 rather, then if you add the inputs x1 plus x2, they should give you a corresponding output of y1 plus y2. Now, a linear system also satisfies the scaling property or the homogeneity property, where if you have an input x that gives you an output y, then if you scale x or multiply it by a scalar value k, it should give you a corresponding output where if you scale y with that same scalar, they would be similar to the outputs without the scaling. Now, when you add the additivity property and the scaling property, that gives you the superposition theorem, where an input gives you an output in one instance, another input gives you another output in another instance. When you scale the inputs and add them together, they would give you outputs reflecting the same scaling. And that is called the superposition theorem. So generally, linear control systems or linear systems obey the superposition theorem. Now, when you look at nonlinear control systems, the input and the output does not have a linear relationship. The relationship is non-linear, and they do not obey the superposition theorem. So you can see a graph of adhesion characteristics on the road where you're plotting against the adhesion coefficient. This is a nonlinear relationship from the graph because it's not reflected by that straight line. Now, you can also classify control systems as time variant and time invariant systems. So when the characteristics of the system do not depend on time, no matter how much time has passed or as time goes on, the system characteristics or the dynamics of the system does not change, then the control system is time invariant. So an instance is 2u of t plus 1. The value of t has no effect on the equation because t is just the operator, the time domain operator. But in time varying control systems, one or more of the system parameters varies with time. So if you look at this equation, 2u of t minus 3t, that part 3t, if you change the value of t multiple times, it would affect the total value of y. Because t is not the time domain operator, it's actually a variable in that equation. Now, apart from this, there are many other types of control systems. You can classify control systems in other categories as well. So let us look at some of them. The first one here is deterministic and stochastic control systems. So if you can determine the output of a control system over time, then it's deterministic. However, if the control systems exhibit some random properties and you cannot accurately determine its output over time, then it's stochastic. You have continuous and discrete control systems. So control systems that operate with continuous signals are signals that exist at every point in time. Then those kind of control systems are referred to as continuous control systems. However, if the control system operates with discrete signals, then it's a discrete control system. So discrete signals do not exist at every point in time. They exist at uniform intervals in time. So maybe after every 1 second or after every 2 seconds and so on. You have classical and modern control systems. So classical control systems are mostly characterized as single input, single output control systems that can take single input and single output. And mostly they are designed using things known as transfer functions. However, modern control systems were introduced relatively recently, and they are categorized by multiple input, multiple output systems. So they take in more than one input and they can give you more than one output. And mostly they are designed using state space techniques. Then you also have robust control systems. So generally, systems would, as we said, systems are nonlinear in nature physically. And when you are operating a system in the real world, there are many disturbances and many nonlinearities that can affect the performance of the system. So robust control systems try as much as possible to make sure that the nonlinearities and disturbances experienced do not affect the performance of the system. That's what robust control systems are all about. Then you have intelligent control systems. So control systems that are interfaced with some form of artificial intelligence, either optimization or machine learning. These AI techniques could maybe select one or more parameters of the control system, or these AI techniques themselves are used as control systems, then those are intelligent control systems. Then you also have adaptive control systems. In adaptive control systems, the operation of the control system changes depending on the conditions that the control system is operating in. So maybe if it's operating in a very cold environment, the control system would adapt itself to work within that environment. And when you move it to a warmer environment, it can adapt itself to work within that environment. You also have predictive control systems. These types of control systems can predict future states of the plant or future occurrences. So they try as much as possible to predict future behavior of the system so that they can adjust preemptively to avoid improper behavior. Then you have optimal control systems. Mostly in these cases, you have a cost function that you're trying to optimize or minimize, which reflects the problem. So for instance, you're trying to minimize energy consumption. So you can represent that as an equation, and the control system will try to minimize the energy consumption. So the performance of the control system is based on the cost function of the objective that you've given the system. And also you have multi-agent control systems. In these instances, the control system controls different parts of either a single system or different systems working together as one or to achieve the same goal. So these are some of the types of control systems we have. And over time, we'll be looking at them one after the other to understand them better. Thank you.